Hello and welcome to Engineering Dynamics. I'm your host, Dr. Walk, and today we are going to be talking about rigid bodies and the three types of motions that are associated with rigid bodies. To understand these types of motions, we need to define what a rigid body is. A rigid body is where all the particles inside of that rigid body, they don't move. They don't change distance from each other. This means that if I can define the linear velocity of one particle within that rigid body, I'm really defining the entire body's linear velocity. So a really good example of this is if you look at this eraser. If I want to describe the linear velocity of it, so if this eraser travels on this track, it is in a translational motion. And if I can explain the velocity of this point, it's going to be the same as the rest of that rigid body, okay? So if I can explain one point's velocity, that means that I've just described the velocity of the entire eraser, right? This point of the eraser is not going to go faster than this one. And if this one is going in this direction, it's not like this one can go in a different direction because of the definition of a rigid body. So that's translational motion, body. The next two motions are a little bit more involved. Let's first talk about rotation about a fixed axis. So we call this pure rotation about a fixed axis. And what this means, think about a real world example. If you think of a boat propeller, you have a shaft, and then you have the propeller itself coming out, those little wings. The wings are going to rotate about the shaft. And what we say in dynamics is that every single particle that touches the shaft is going to be fixed. It's not going to move. But all of the particles away from the shaft, so the big propeller wings, they are going to be constantly rotating or in pure rotation about that fixed axis. What does that look like when we draw it out? If we take a circle, and if this is like our propeller, and our shaft would be in the middle here, this is going to be fixed, okay? And say we want to describe the motion of a particle out here. So I can describe this, any point that lies on this axis here is going to have zero velocity. It's not going to move because it's a fixed axis, okay? So that means that every other point around it has to be in pure rotation about the fixed axis. So although I picked this point here, I can pick any point I want. And this calculation that I'm going to show is going to be the same for everything, okay? So, but for right now, let's just focus on one point at a time. So velocity is always what to the curve? If you said tangent, you are correct. So velocity is always tangential to the curve. So let's draw a velocity here. And why don't we go ahead and assign some letters to these dots that we made? Why don't we make this B and this A randomly? And I want to, let's also draw a position vector here. You can also tell me that since the velocity is tangential to the curve, the angle between the position vector and the velocity vector has to be a 90-degree angle. So this is R A with respect to B. If you are not familiar with this notation, think about a common situation that you would have locating point P. If I said that this is RP, you wouldn't second guess it. You'd be like, yep, that works. If I labeled this point O, and then I said that this is a vector R to P relative to O, Would that make sense? The reason that we don't, or one of the reasons that we don't normally declare or define that this is P relative to the origin is because we would be representing every single vector that is relative to an absolute origin with O. That's a lot of writing. So when you see R with respect to P, it is assumed that this is relative to an origin. Okay. When we move to rigid bodies, that origin is actually going to be a part of another rigid body. So let's look at an example. Say if you had a 4-bar linkage, or I mean anything, right? Like let's just pick this out. If I labeled this A and B, and I could label this O or O prime. If I want a vector like this, that would be RA with respect to O. If I have a vector here, this is going to be RB with respect to A. And again, if I go here, it would be a vector RB with respect to O prime. The way you remember this is that the letter that comes first is the head of the vector. The letter that comes second is the butt of the vector. Okay, so now that we understand this, let's go back over to our drawing here. And we said we have a position vector, A relative to B, and we also have a velocity vector. My question to you is, when we describe the velocity of point A, what do we need to consider? What are the terms we need to consider? Well, you need to ask yourself, what is the main difference between a rigid body and a particle? All right, if you said the main difference is going to be angular momentum or angular velocity, you are correct. And a way to visualize this, let me see if I have something over here. This will work. So if I have this rigid body and I want to explain its rotation about a fixed axis, if I rotate it this way, that's a different motion than if I rotate it this way. And that's a different motion if I rotate it this way. So now we have to consider omega. Omega is this angular velocity. Okay, a particle is not going to have a moment of inertia. It's not going to have a mass distribution. Okay, so now we have to consider, if I want to define a velocity, a velocity A, I would say that it's equal to omega cross RA with respect to V. Now, if I write this, so this might look a little weird. If we write it in scalar form, I bet it doesn't. We know that. We know this formula because it comes from, if I draw, let's see if I do this, let me see if this color will work. That might be a little too light. So if we draw another R, say maybe this is R prime, the angle between these two is theta, and this here is S for arc length. We know that S equals theta equals R theta, okay? So if we simply take the derivative of this, the derivative of position is velocity, the derivative of theta is omega, okay? And R is constant, so that can just stay as R, okay? So this is a perfect equation to represent the velocity of A in a scalar form, but sometimes we want it in vector form. And that's just because it makes calculations easier. I know that it sounds like I'm making it more difficult, but it's actually not. It's actually easier at some points to use a vector. And that's because later on, when we start solving more complex problems, we're going to have a lot of unknowns. And one scalar equation can only have one unknown in it, okay? But so in a vector equation, right, it has components. So if it's a two-dimensional vector equation, then you actually can break that up into two equations. So you have, how someone says like, oh, you have two unknowns, you need two equations. Well, in vector form, you get more equations with less work, okay? So that's why I really like vector form. So how did I get from here to here? Well, I'm gonna say that I have to create a coordinate system first. So let's take a look at, I think it's easiest to see using polar coordinates, which is using the unit vectors radial and transverse. So here is the radial unit vector ER, and here is the unit vector E theta for transverse direction. And E theta, so you could kind of write it like this: E theta equals ER cross, this one is going to be EZ, because this point here would be EZ. I'm getting all of this by the right-hand rule. If I stick my thumb out in the Z direction, and I take my fingers into the radial direction, my curl of the fingers would be in the direction of theta. So think about this. If you have I cross J, you should get a unit vector K. So if I cross J cross K, I will get I. Here you are crossing Z cross R, so that means you're going to get the third, which is theta. So if you haven't caught on yet, let me just talk this through. The cross product is going to give you the orthogonal to both of these. So these two, the orthogonal or the third axes that are perpendicular to both of these, would be the third one. So in this case, we have Z and R, which is radial. Your perpendicular axes to both of these, or this plane, is going to be theta. Okay, that was a long-winded explanation, but I hope you understood it. Okay, so this describes our point A as if it was in pure rotation about a fixed axis. So if you were looking at a merry-go-round and you spun it, the part that is sticking up is your z-axis, and then the plane that you're looking down where the movement is occurring is going to be ER and E theta. This equation here, either vector form or scalar, these are both totally valid. Both of these will describe any point on this body. It will describe its velocity about v. Okay. What happens if this merry-go-round turned into a car tire or a bicycle wheel? That means that it's spinning, right? So now I'm looking at it in this coordinate system, and z is still going in and out of the board. So now it's spinning perfectly, but it's also traveling. So now you have a linear component as well. So now this only describes the rotational parameter of the linear velocity of A. Now you need to describe, because as this guy rolls, right? Oh, I'm so not a good drawer. I'm sorry, but I hope you get the idea. As this thing goes along, point B, the axis, is going to move along with it in a straight path. So if A is undergoing pure rotation about a fixed axis, meaning you're just spinning your tire wheel. You're not actually going anywhere. So say you have training wheels on and you get stuck in a hole, and your training wheels are on the side of the hole and your wheel is just spinning and spinning and spinning and spinning, but you are actually not traveling anywhere. These are these equations. But if you are traveling, now you have to take into consideration that linear translation. So now you move into planar motion. So now to describe VA, we're still going to describe its pure rotation about a fixed axis because our wheel is still turning about the center axis, right? But now we have to add the term VB. This will take into consideration how this point B as in boy, is traveling in a transverse manner. So now you have your planar, okay? So I think that describes the three types of motion when you are looking at rigid bodies pretty well. And I'll pause it here. And then in our next video, let's go ahead and do an example to where we can apply all of these equations. Thank you so much. I hope you like this video and you consider subscribing.